For this video, we're going to be discussing scatter plots and lines of best fit. So what is a scatter plot? A scatter plot is just a type of graph that compares two sets of data. One set of data is represented by the x-axis, which hopefully you remember is the horizontal axis, and the other is represented by the y-axis, so our vertical axis. And all we're going to do is we're going to put points on the graph comparing the x and y data. So for example, if I gave you a table, x and y, and I said x was 1, 2, 3, and y was 2, 3, 4, to make a scatter plot, I just turn these paired pieces of data into ordered pairs, and I'm going to plot them on my coordinate plane. So, I've got x is 1, 2, 3, we'll put 4 and 5 on here, and then 1, 2, 3, 4, 5. We'll just go up like this. To make a scatter plot of this data, I just take my ordered pairs and I plot them. For example, I've got the point 1, 2, so I just go over 1, up 2. There's a point. The point 2, 3, so over 2, up 3, there's a point. And the point 3, 4, over 3, up 4. Notice that all I did is I took my paired data from my table, turned them into ordered pairs, and plotted them. There we go. Now I have a scatter plot. It's really very easy. Scatter plots just look like points on a graph. That's all there is to them. All right? So, what if, for example, I wanted to make a scatter plot for this given data here, where we have the number of hours of sleep a student is getting being compared to their score they get on a math test. So what I'm going to do is I'm going to make one of these my x-axis and one of these my y. So I'm going to say that hours of sleep, that's the x, and the math score, test score, that's the y. So I'm going to make a coordinate plane. I'm going to say that the x-axis down here, that's the hours of sleep. And the y-axis on the side, that is the test score. So now all I'm going to do is I'm going to take these pieces of data that go together. I'm going to make an ordered pair. So I'll show you, this is the completed scatter plot. You see all these little points. These correspond to this table. For example, if a student gets 9 hours of sleep, they get a math test score of 93. So I can go over to 9, I can go up, okay, there's 93. Now notice there's another dot here because there was another student who slept for 9 hours, got a test score of 91. A student who sleeps 5 hours gets a test score of 70. For 6 hours of sleep, we have 3 different test scores that students get, a 68, a 77, and an 81. And then the rest of these points also come from paired data from this table. So you can see to make a scatter plot, all we do is take the data from the table and make them into points on a graph. Now, when we're talking about scatter plots, we have this word called correlation that we have to think about. And all correlation is it's a measure of how closely related two sets of data are. The higher the correlation, the closer the data sets are to forming a straight line. So, for example, I'm going to show you two different scatter plots here. Here's one, and here is the other. Now this scatter plot, you can see the dots are kind of all over the place. If I tried to draw a straight line through them, well, I could draw all sorts of straight lines. None of them quite go through all those dots. They all kind of just go everywhere. In fact, the dots kind of don't form any sort of line at all. So this is what we would say would be like no correlation. On the other hand, at this scatter plot, notice how my dots are all very, very tightly clustered together. And it'd be pretty easy for me to draw a straight line that doesn't necessarily hit all the dots, but goes really closely through them. So this we would say has strong correlation. 2 R's in correlation. All right, so the closer the dots are to forming a straight line, the stronger the correlation. So let's look at the different types of correlation I could have. Now, in our first graph here, you notice that my data points are all really close together. They all form pretty close to a straight line. So this is going to have strong correlation. But notice that as my x gets bigger, my y is getting smaller. All right, that means that this line has a negative slope, so this is what we call a strong negative correlation. All right, because the line slopes down, it's a negative slope. Because my data points are close together, that is what makes it a strong correlation. Compare that to over here, where my points are not all that close to forming a straight line. They kind of are. We can notice the data kind of trends downwards. So this is what we would call a weak negative correlation. Because we could see the line kind of goes down, but our dots aren't all that close together. So it's still a correlation, but it's weak and it's negative. This table over here, well, can we draw a line? We could draw this line, but we could also draw this one or this one. My dots don't form a line at all. This is what we would call a no correlation graph. Now down on the bottom here, notice that the points in these two graphs tend to trend upwards. As x gets bigger, y also gets bigger. So these both have positive correlations, as does this one. Oh, my pen didn't want to write. As does this one at the end here. But notice, similar to this graph up here, this one here, my points aren't all that close together, so this is what we'd call a weak positive. These ones are pretty close together, so we'd call this a strong positive. And these points actually form a perfect straight line, so we would call this a perfect positive correlation. We could also have a perfect negative correlation if they all followed a straight line and they're going down. So hopefully you see the idea that correlation is simply how close the points are to forming a straight line. All right, so let's try and determine the correlation of each set of data here. First you try it, and then I will help you. All right, so let's take a look here. If we look at part A here, we can notice that our dots aren't all that close together, but the data does kind of trend where as x is getting bigger, y is getting smaller. So that's what we're going to call a weak negative correlation. In this graph, our dots are all very close together, close to forming a straight line, so we're going to call it strong. And because x gets bigger and y gets bigger, this is a strong positive correlation. And then our final graph down here, my dots are kind of all over the place, so this is a no correlation graph. All right, so hopefully by now you get the idea of correlation. Our third and final concept that we need to talk about is the line of best fit. So a line of best fit is a line that can be used to model data. And it's simply a line that is drawn that is as close to the middle as data as possible. And it can be used to predict data values. And you do not need to worry about this last little line here. We don't need to talk about the correlation coefficient. So, to draw a line of best fit, all I do is I try and draw a line that is going to fit as closely as it possibly can with all the data in the set. All right, so kind of like this. It's as close as possible to being in the middle of that set of data. Now notice, it does not have to touch all the data points, and it actually doesn't even really have to touch any of the data points. It just has to be as close as possible to the middle of the set. I'm going to show you in our next example that we can use this to make predictions about further information in our data set. So let's take a look at that. So here we've got a scatter plot describing the percentage of households with cable television based on the year from 1988 to 2000. All right, and you can see the scatter plot's been drawn in here, and so has the line of best fit. Notice how the line of best fit touches some of the data points, but not all of them. And we're being asked to use this line of best fit to predict the percentage of households with cable in the year 2000. So all I have to do that is, well, I've got this line of best fit drawn. I'm going to go to the year 2000, and I'm going to go up and see where does it cross that line. It crosses right here. So now I can go over 72, so my answer is 72%. So, based on our data, about 72% of households should have had cable TV in the year 2000. So that's how we use a line of best fit to predict new values. We draw in our line of best fit to fit the data as best as possible, and then find points along that line to make predictions. So your try-it problem is to use this line of best fit to predict the number of words per minute for 8 weeks of practice.